Today we are going to learn a second method for finding volumes of solids of revolution, and this method is called the shell method. So here is why we want to use the shell method. We want a different method. So suppose we take this region that's bounded by 2x squared minus x cubed, and we try to rotate this about the y-axis. So as they have indicated here, they're spinning it this way. And recall that if we're using our disk method from last time, what we would have to do is we'd have to find the outer radius, we'd have to find the inner radius. And in either case, that's going to mean you have to take this expression and you're going to have to solve for x. And call me crazy, but I don't think that's very easy, nor the best way to do it. So man, wouldn't it be nice instead if we could slice it this way and then rotate those things around the y-axis? And think what would happen if you took this little slice and you spun it about the y-axis. You're going to get hollow cylinders. That's why this method is called cylindrical shells, because we're going to learn a method where you can slice this way. Because then we would need to know the height of a slice, and that would just be this equation. We'll also need to know some other stuff, but let's first sort of look at some pictures that describe what this is. So this is called the method of cylindrical shells. A great thing to think about here is it's a little bit like Russian nesting dolls. Matryoshka. So you have, outer doll, inner doll, inner doll, inner doll. But the idea is you take this region from A to B, you spin it about the y-axis, and unlike the previous method, you slice parallel to that axis. Make little rectangles, and then spin those rectangles. So this is a picture of what the actual solid would look like. And this is a picture of what would happen with those little rectangles being spun. You can kind of see the whole nesting doll thing. So the thing that we want to do is we need to find an equation for the volume of a slice. And keep in mind that each slice is a cylinder with a hole, or a hollow cylinder. So here is an arbitrary hollow cylinder, and we're going to call this V sub I, and it's going to equal the volume of one shell. One very boring doll. So, the volume of a cylinder is pi r squared h, so the volume of the outer cylinder will be pi r2 squared h. And the inner cylinder will have volume pi r1 squared h. And this derivation is pretty clever, but at least that first should be pretty obvious. You find the area of the outer cylinder and you took away the inner cylinder. Now take out the greatest common factor of pi h. So we'll have pi h times r sub 2 squared minus r sub 1 squared. And now factor that expression. There we go, expression factored. Now we're going to do a clever thing here. We're going to multiply this by 2, and before you protest and say, oh my gosh, that's totally not going to be okay, if I also take this r2 plus r1 and divide it by 2, I've changed nothing. So clever changing of nothing that occurred. Now notice a couple things. This is the average of your outer and inner radii, and this is delta r, as in how much your radius changed. So another way to write this, you rename this thing, call that r. See how it's called r in the picture as well. So that is the same thing as 2 pi h r delta r, or rewritten just a little bit differently, 2 pi r h delta r. This is your circumference, that's your height, that's your thickness. And so in terms of your picture, if you go back to that picture where we were spinning something, you redraw it down here. All right, so if I'm taking this random shell and I'm spinning it about the y-axis, the radius, or the distance from the axis of rotation out to the slice, will be x, and the height will equal f of x. Now these things are subject to change if you have an axis of rotation that's not the x or y axis, that will change the radius. And if you have the region between two curves, your height will not just be f of x. But in general, here's the formula. So in general, the volume will equal 2 pi integral from a to b, let's say r of x for your radius, h of x for your height of a slice, dx, which in the simplest cases is 2 pi a to b x, f of x, dx. And even though this method is less obvious than the previous one, it turns out that the integrals that result are often simpler. So find the volume of the solid obtained by rotating about the y-axis, the region bounded by sine of x squared and y equals 0, between 0 and pi. So for this one I would probably have given you a picture, but here's what it looks like. Root pi's there, and the curve does something like this-ish. So you want to take that and you want to spin it about the y-axis. So since it's not easy to solve for r out and r in, we try shells. So we take these kind of shelly things and we spin them about the y-axis. So the general formula for that is 2 pi a to b radius, height, thickness is dx. So circumference, height, thickness. So the radius is the distance from your axis of rotation out to a random slice, that's just x. Your height, how tall each slice is, would be given by sine of x squared. So now your volume is 2 pi. Your slices begin at 0, they end at square root pi. So 2 pi x times sine of x squared. And now we just need to integrate this. So use a u substitution. Let's let u equal x squared. du is 2x dx. So half du equals x dx. And let's change our bounds because it really is easier. If x equals 0, u equals 0. And if x equals square root pi, u is just equal to pi. So that becomes 2 pi times 1/2 the integral from 0 to pi sine of u du. Or just pi times, now the antiderivative of sine will be negative cosine, and evaluate that from 0 to pi. So pi times negative, well, cosine of pi is -1, minus cosine of 0 is 1. So I believe that makes 2 pi in the end. So the volume of that solid, when you take this region and spin it about the y-axis, that's 2 pi. All right, next let's deal with one where we have our height function looking a little bit different. So find the volume of the solid obtained when you rotate 3 plus 2x minus x squared and x plus y equals 3 about the y-axis. So first you have to graph these, and while graphing x plus y equals 3 is not very hard, just express it as y equals negative x plus 3 and use the slope and the intercept. Graphing the parabola, I think the best method is to complete the square. So take out the negative, x squared minus 2x, and now we add in 1, we've actually added negative 1, so we also add 1 there. And that becomes negative parenthesis x minus 1 squared plus 4. So now graphing these two functions. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, let's start with the parabola. So you go over 1 to the right and up 4, that's your vertex. Down 1 over 1, down 3 over 1. So there's your parabola. Negative x plus 3 starts at 3 and then has a slope of negative 1. And it looks like your intersection points are x equals 0 and x equals 3. Okay, so I'm taking this region and I'm slicing it parallel to the axis of rotation as being spun around the y-axis. Once again, r out, r in, not super easy. You'd have to solve that expression for x, and man, it's not going to be very much fun. So we're going to do shells. Your radius is your distance from your axis of rotation out to your slice, that's just x. And the height here, well, that's just the top curve minus the bottom curve. So that's the 3 plus 2x minus x squared minus negative x plus 3, which is the same thing as 3x minus x squared. So now your volume is 2 pi integral from a to b, radius, height, delta x. So your slices begin at 0, they end at 3. Your radius is just x, your height is 3x minus x squared. So that's the same thing as 2 pi integral 0 to 3, 3x squared minus x cubed. And now antidifferentiate, and you're going to have the antiderivative of 3x squared is x to the third minus 1/4 x to the fourth, evaluated from 0 to 3. So that's 2 pi times 27 minus 81/4. Getting a common denominator, it's 2 pi times 108/4 minus 81/4, or 2 pi times 27/4, which gives us 27 pi over 2 for our final volume. So the point being for these is that you use this method when the disk method proves too difficult. Although in many instances, the integral that results from this method, like say that, it's actually easier to solve that in many cases. So sometimes both methods work and sometimes one method is better than the other. Let's just move on with that. Let's discuss that in the next example. So suppose you have this region bounded by negative x squared plus 6x minus 8. Which method is preferable when you rotate this region about the following axes? And then we're going to set up, but don't solve, the resulting integrals, which you would use to find the volume. So first, let's complete the square. So negative parenthesis x squared minus 6x and minus 8. So we're going to add 9. We actually added a negative 9 because of the negative in front of the parentheses, so we're also going to add 9 there. Negative parenthesis x minus 3 squared plus 1. 1, 2. So that's a parabola that's been upside down, moved over 3 and up 1. It's going to cross the x-axis at 2 and at 4. And I probably should have specified also by y equals 0. So the region we care about is that little region there. Okay, so first of all, if we're going to spin about the x-axis, you ask yourself, would it be easier? Disk method says we slice this way. Shell method says we slice that way. So which way would it be easier? Do you want to have to find r out and r in, or just the height? And the answer is just the height. In this case, the shell method is easier. And so your volume is an integral from, well, 2 pi a to b r of x h of x dx. So your a is 2, your b is 4, your radius, distance from axis of rotation out to random slice, is x. Your height is just the curve itself, so negative x squared plus 6x minus 8. And so that's the same thing as 2 pi times the integral from 2 to 4 negative x cubed plus 6x squared minus 8x. You don't have to solve that, but that's the thing that you would solve to get the volume. I'd also be okay if you left it at that step, the step before the one that I circled. That's also fine. But the point is, for that problem, shells is easier. So about the y-axis, shells is better. So same region, but we're going to go about the x-axis this time. So that was 2, this was 4, at 3 we were at 1, so picture looks something like that. And you took this region and you're going to spin it about the x-axis. So you ask yourself, do you want to slice this way? Or do you want to slice that way? So doing the purple one would involve solving that equation for x. Yeah, don't want to do that. So probably the first way. And that first way, you would think, if I do that, my cross sections are circles. That's the disk method. So in this case, the washer slash disk is the better method to use. And remember there, your volume is an integral from a to b, pi times your radius squared. You're adding a bunch of circles. So that's pi. The integral is still from 2 to 4. And your radius is negative x squared plus 6x minus 8, that whole quantity squared. Squaring that would be a huge pain, but tedious, not impossible. That's how you would find the volume. Now, the first examples we did with the shell method, we rotated about the y-axis. Now, what if we rotate about the x-axis? What's going to change, and when do we want to do this? So suppose we have some region that does some kind of funky thing. So it's expressed as x equals f of y. We want to rotate this region about the x-axis. So there's our slices. We're going to get those shell doll things again. Now the difference here is that your radius will be a function of y. It's often going to be y itself. Distance from axis of rotation up to your slice is y. Your height function will just be the function of the curve, with some differences if you have two curves, but in general. So the difference here is that you will have an integral from c to d, those are y values, 2 pi y f of y dy. And this is useful when solving for y is hard or impossible. All right, let's use cylindrical shells to find the volume of the solid obtained by rotating the region under y equals root x from 0 to 1 about the x-axis. So root x, 1, 1, is approximately like this. Okay, so region under that from 0 to 1 means we're looking at this part, and we're going to spin it about the x-axis. Now something to note here is that the disk method is actually easier, so we're going to use that to check our answer. But if we use the shell method, we have to slice parallel to the axis of rotation. So our slices go like that. And you have to think, okay, my volume is 2 pi integral from some c to some d, radius, height. Okay, now the radius in this case, distance from axis of rotation out to random slice, that's just y. Now the height here is a bit tricky. Top curve minus bottom curve. Your top curve is 1, not very curvy, minus the bottom curve, which is the same thing as x equals y squared. So 1 minus y squared. So your volume equation, and also your slices, begin at y equals 0, they end at y equals 1. So 2 pi integral 0 to 1 y times 1 minus y squared dy. So that's 2 pi integral 0 to 1 y minus y cubed, or 2 pi times y squared over 2 minus 1/4 y squared from 0 to 1, or 2 pi times 1/2 minus 1/4, and 1/2 minus 1/4 is 1/4, and 1/4 times 2 makes 1/2 again. So your final answer is pi over 2. So that was the shell way. Just to show you the difference, let's show you what the disk way would do, and that does yield the same result. The disk method would be the volume is pi integral a to b radius squared. And in that case, we're slicing perpendicular to the axis of rotation like this. Notice that the radius is just root x. That's pi integral 0 to 1, technically x values, root x squared. And holy moly, you just get pi integral 0 to 1x. Super easy, right? Pi times 1/2 x squared. And once again, we get pi over 2. So some problems you can do both ways, and sometimes one method is preferable, even though technically both of them work. All right, this one, you're really going to have to use the shell method because the disk method is just too hard. So find the volume of the solid by rotating the region bounded by these two curves. X plus y is 4, and x equals y squared minus 4y plus 4. All right, now to graph these, personally, I find this one easier as negative x plus 4. Now the second one, kind of nice, the square is already completed. This is x equals y minus 2, the quantity squared. So here is what our picture looks like. 1, 2, 3, 4, 1, 2, 3, 4. All right, our line begins at 4, slope -1. Okay, so there's your line. Now, y minus 2 squared is like a sideways parabola moved up 2. And you can verify for yourself by plotting points that it looks like this. So that region between them, this stuff, is the stuff we're spinning about the x-axis. So think about your slices. The radius of a slice is just going to be y, as in distance from axis of rotation out to slice. Height of slice will be top minus bottom. So the top curve is 4 minus y. The bottom curve is y squared minus 4y plus 4. So simplifying that a little bit, that's the same thing as negative y squared plus 3y. Great. Okay, so now my volume will be 2 pi integral, so we'll say lowest y value is 0, highest y value is 3, radius, height, dy. So the radius is y. The height is negative y squared plus 3y. So that's negative y cubed plus 3y squared dy. So 2 pi negative 1/4 y to the 4th plus y cubed, evaluated from 0 to 3. So that's negative 81/4 plus 27. And getting a common denominator, that's 108/4. So that's 2 pi times 27/4, which is 27 pi over 2. All right, now let's see what happens when you rotate about a line that is not the x or y axis. So when you had two curves, the radius was either x or y, but now this one, when you move the rotation, that's going to change the radius. So here we go. Y equals root x. 1, 2, 3, 4, 1, 2, 0, 0. 1, 1, 4, 2. X equals 2y, same thing as y equals x over 2. So slope 1/2 will look like this. And we're going to rotate about the line x equals 5. So there's your line of rotation. That's what you're going to spin around. So you got some random slice here. What is the distance from that random slice to the axis of rotation? So that distance will be 5 minus x. The distance from here to here is x. The total distance is 5, so 5 minus x is my radius. My height function, top curve is root x, bottom curve is x over 2. And your slices begin at x equals 0, they end at x equals 4. So the volume is 2 pi, integral 0 to 4, radius 5 minus x, height root x minus x over 2. Okay, now expand and go. 2 pi integral 0 to 4, so you have 5x to the 1/2 minus 5 over 2x minus x to the 3/2 plus 1/2 x squared. And the arithmetic is a little bit tedious, but it's not ridiculous, but it's a little bit of a pain. 2 pi, the antiderivative of 5x to the 1/2 is x to the 3/2 times 2/3 makes that 10/3. X squared, 1/2 makes that 5/4. 2/5 x to the 5/2, and then plus a 6th x to the 3rd. Okay, let's plug all of our numbers in. So 2 pi times 10/3. Now 4 to the 3/2 will be 2 to the 3rd, or 8, minus 5/4 times 16, minus 2/5 times, so square root of 4 is 2, 2 to the 5th is 32, plus 64/6. And let's just reduce and tell you what it adds up to. 2 pi times 80/3 minus 5 times 4, which is 20, minus 64/5 plus 32/3. And all of that gives you 136 pi over 15. It's really easy to make an error in your arithmetic, so you can use a calculator if you want to sort of like find common denominators and just double check that you multiplied correctly, but still show all of your work. Okay, so now let's rotate about a horizontal line. So x equals 2y squared and x equals y squared plus 1. So we'll have two sideways parabolas. 1, 2, 3, 4. 1, All right, this first one will go through the origin. When you input y equals 1, you get x equals 2. Same thing for y equals -1. So that one is going to be kind of a narrower sideways parabola. Y squared plus 1, when you input y equals 0, you get x equals 1. When you input y equals 1 and -1, you get 2 for the x's, so it looks a bit like this, a bit wider parabola. So we're going to spin this region about the line y equals -2. All right, first thing to figure out is what is the radius going to be? So what is the distance from here up to a random slice? Well, let's think. Is it 2 minus y? Would that work? Don't think so, because when you were, say, at that y value of -1, it'd say your distance of 3. It has to be 2 plus y. So if you take 2 and you add the y coordinate, it tells you how far away. It's like if that y coordinate is -1, you're a distance of 1 away. If that y coordinate was 0, you're a distance of 2 away. If your y coordinate was 1, you're a distance of 3 away. That definitely works. And then the height will be the rightmost minus the leftmost. So y squared plus 1 minus 2y squared, or 1 minus y squared. And once you get the setup, the rest of it's easy. The hardest thing is setting these up. So now your volume will equal 2 pi integral -1 to 1, 2 plus y times 1 minus y squared. And here's where students get a little bit tripped up, that they would like to use the trick where you can go twice the integral from 0 to 1. But the function inside your integral sign is not an even function anymore, even though that picture has symmetry. So you can't use that trick, you have to use both numbers. So sorry. 2 pi integral -1 to 1, 2 minus 2y squared plus y minus y cubed. So that's 2 pi times 2y minus 2/3 y cubed plus 1/2 y squared minus 1/4 y to the 4th, evaluated from -1 to 1. So that'll be 2 pi times 2 minus 2/3 plus 1/2 minus 1/4. All that minus -2 plus 2/3 plus 1/2 minus 1/4. And a bunch of stuff will cancel. 2 pi times, well, we're going to have a 2, another plus 2, minus 2/3 and minus 2/3. But the 1/2s cancel and the -1/4 cancel. So that's 2 pi times 4 minus 4/3. Or 2 pi times 12/3 minus 4/3. So 8/3 times 2 is 16, so 16 pi over 3. There you go. And if you want to do extra practice, what I would suggest doing is just picking some problems that are probably odds, setting up the integrals, and using a calculator or Wolfram Alpha to find the answer, and then just seeing if you have it right, and hope that in the event that you actually do a problem, you can do all the arithmetic correctly. But the setup is the hardest part. Once you get that, the rest of it, as long as you're careful and you're neat, should be okay. And just like in the previous lesson, we proved one volume formula using the disk method, we're going to prove a volume formula using the shell method. So we're going to use cylindrical shells to find the volume of a right circular cone with height h and base radius r. And maybe you've seen this before in a calculus class or a geometry class, but the volume of a cone, as described, is pi over 3 r squared h. And we're going to actually prove why it is what it is. So here is how you do that. So height h, radius r, connect with a line. If you take that triangle and you spin it about the y-axis, that makes your cone. And you can get an equation of this line by noticing that it has y-intercept h, so plus h, and the slope is negative h over r. So you would go down h, run r, rise over run. And so we're going to slice it this way and add up all the slices, and we're going to use cylindrical shells to prove the volume is what it is. So the volume is 2 pi. Now my slices begin at 0 and they end at r. The radius, distance from there to there, is x. The height of each slice is negative h over r x plus h dx. That dx tells you that x is your variable, everything else, those are all constants. So 2 pi integral 0 to r negative h over r x squared plus hx dx. Now the antiderivative will be negative h over r times 1/3 x cubed plus h times 1/2 x squared, evaluated from 0 to r. Now plug in your stuff. So I have 2 pi negative h times r cubed over 3r plus h times r squared over 2. Now in that first term, and plugging in 0 just gives us 0. That first term, what we really have is negative h r squared over 3, because one of the r's cancel, plus h r squared over 2. Look, those are like terms. We can get a common denominator, we can combine them. 2 pi times negative 2h r squared over 6 plus 3h r squared over 6. That'll be 2 pi times h r squared over 6, which when you multiply them and reduce is pi r squared h over 3, which is the formula that we should know and love. And so once again, this is why that geometric formula is what it is.